Okay, in this video we're going to be looking at alternating series. This is section 5.5. So definition of an alternating series. Any series whose terms alternate between positive and negative values is called an alternating series. For example, the sum n equals 1 to infinity of negative 1 to the n plus 1 times a sub n, that's equal to a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, etc. It keeps going. Or it looks like the sum n equals 1 to infinity of negative 1 to the n of a sub n, and that's going to be equal to negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4, etc. So let's take a look at example of the harmonic series, not quite the harmonic series, but the harmonic series with an alternator. So we'll look at the sum n equals 1 to infinity of negative 1 to the n plus 1 all over n. So we'll evaluate at 1, you're going to have negative 1 to the second power, which will be positive 1 over 1, plus it would be negative 1 to the third power, which would make it a negative 1 over 2. Then you'll see the alternation. So for n equals 3, we'd have 3 plus 1, which is 4. Negative 1 to the fourth power would be a positive 1 over 3, etc. Okay. Now we can also have an alternating series where it is a negative 1 to the n, so we'll take a look at that. So negative 1 to the n over n, and it doesn't have to be over n, that just as an example here. So negative 1 to the first power is negative 1 over n, which is 1. Okay, and then n equals 2, then we have negative 1 squared, which would be positive 1 over 2. And then negative 1 to the third power would be negative 1 over 3, etc. And it just keeps on going. Okay, so this is what an alternating series looks like. Sometimes, they might use like a sine or a cosine that does alternation. So, but typically you're going to have negative 1 to the n, negative 1 to the n plus 1, sometimes negative 1 to the n minus 1, but typically it's either n or n plus 1 as the exponent. So here's the alternating series test. So we have an idea what an alternating series looks like. An alternating series converges if the following two conditions are met. The first is the limit as n goes to infinity of a sub n is equal to 0. And then the second is 0 is less than or equal to a sub n plus 1, which is less than or equal to a sub n, for all n greater than some natural number n. And essentially that's just the sequence is decreasing. So, and it doesn't have to decrease right away, but eventually it needs to be decreasing. So an idea of the sketch of the proof, let's consider the sum n equals 1 to infinity of negative 1 to the n a sub n. So we're going to look at s of 2n, and so that's going to be all the even partial sums, so s2, s4, s6, s8, etc. So what that looks like is the first term will be a negative, so negative a1 plus a2 minus a3, all the way out to the last three terms, a sub 2n minus 2 minus a sub 2n minus 1 plus a sub 2n. We can go ahead and regroup this, and we'll regroup it. Well, we're just going to put some parentheses around it. So we got parentheses negative a1 plus a2 plus negative a3 plus a4, all the way out to negative a2 sub n minus 1 plus a sub 2n. And then we're going to make the assumption that this is decreasing the entire time. If it's not decreasing the entire time, just start where it's decreasing, and then who cares about the first n terms? They're finite. That's not going to affect whether the series converges or not. So each pair I have here is non-positive. Because of the decreasing, a1 would be greater than or equal to a2, and so the best case scenario, I guess, is they're equal to each other, so they'd be 0. But they're going to be non-positive, and so this means that s of 2n is monotonic decreasing. Okay, so it's getting smaller as we continue to add more terms. Each term we add is going to be non-positive, so that's going to give us the monotonic decreasing. We can regroup this and say s of 2n is equal to negative a1 plus a2 minus a3 plus a4 minus a5 plus dot 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 a sub 2n minus 2 minus a sub 2n minus 1, and then plus a sub 2n. Since a sub n is decreasing, is a decreasing sequence, each grouped pair and a sub 2n are non-negative. So s sub 2n is going to be greater than or equal to the very first term, negative a sub 1. So s of 2n is bounded from below. And so we have a theorem that talks about monotonic and bounded sequences. Specifically, we're going to be looking at monotonic decreasing and bounded from below will converge. So we're only looking at the evens, so the limit as n goes to infinity of s of 2n, we're going to say, because of that theorem, we'll call its limit L for some real number L. Since we can write s of 2n minus 1 as s of 2n minus a sub 2n, the limit as n goes to infinity of s of 2n minus 1, that's all the odd partial sums, that's going to be equal to the limit as n goes to infinity of s of 2n minus a sub 2n. Well, we just said that the limit as n goes to infinity of s of 2n is equal to L, and we're making the assumption that the limit as n goes to infinity of a sub n is equal to 0. So if a sub n is going to 0, certainly all the even terms would need to go to 0 as well. So we've shown that all the odd and all the even partial sums converge to L, and so we can conclude that the sum n equals 1 to infinity of negative 1 to the n, a sub n, converges to L. Okay, so we're going to look at a couple examples, and then we'll have another video or two working out some more examples with the alternating series. So let's go ahead and look at the sum, n equals 1 to infinity of negative 1 to the n over n. And so here we're just going to determine whether this converges or diverges by the alternating series test. So the two things we need to check is the limit of the seed sequence goes to 0 and the sequence is decreasing. So your seed sequence is 1 over n. The limit as n goes to infinity of 1 over n is equal to 0. So that's the first condition. The second condition is we need to show that an plus 1, which is 1 over n plus 1, is that less than or equal to an, which is 1 over n. And that's certainly true. So both those conditions are met, and so we can say that this series converges by the alternating series test. Okay. So let's go ahead and look at another example. We're going to look at the sum n equals 1 to infinity of negative 1 to the n over n squared. And so our a sub n is going to be the 1 over n squared. That's our seed sequence. So the limit of our seed sequence is going to 0. So the first criteria of the alternating series test is met. And now we need to show decreasing. So a sub n plus 1 is equal to 1 over n plus 1 squared. So is 0 less than or equal to 1 over n plus 1 squared, that's the a sub n plus 1, that is less than or equal to 1 over n squared, which is your a sub n. So we have our decreasing. And so both of those conditions are met. We have this limit of the seed sequence is 0, and we've also have the sequences decreasing. And so that is enough to show us by the alternating series test that this is a convergent series. Now we're going to look at these two series again, I think in the next video when we talk about absolute convergence, where we look at the absolute value of the seed sequence. Well, it's not, we look at essentially just not the absolute value of the seed sequence, we just look at the seed sequence without the alternator. If that sequence, or if that series converges, then we have absolute convergence. So we'll get into that in more detail in the next video. Okay, let's look at another example. So we're going to look at the sum n equals 1 to infinity of negative 1 to the n plus 1 times n plus, the square root of n plus, try it again, the square root of n plus 1 divided by the square root of n plus 3. Your seed sequence is the square root of n plus 1 over the square root of n plus 3. So first thing we're going to do is we're going to look at the limit of the seed sequence. That is infinity over infinity. So you have a variety of techniques. You can factor out the highest exponent of n. You can apply the L'Hopital's rule. Let's see which one we apply. Well, it looks like we're going to apply L'Hopital's rule. Okay. And so that limit is going to be 1. All right, so because this limit is not 0, that means that alternating series test doesn't apply. So the alternating series test does not apply. All right, and when that happens, usually you're going to look at using the nth term test for divergence. So if we look at the limit as n goes to infinity of -1 to the n plus 1 times the square root of n plus 1 over the square root of n plus 3, that limit is not going to be equal to 0. It's actually going to oscillate between +1 and -1 because of that alternator. And so that series, this sequence does not converge to 0. It doesn't converge at all, actually. And so if the a sub n, in this case with the alternator, if that limit doesn't equal 0, then the nth term test says this is going to diverge. Okay, so the nth term test for divergence, or in this case I'm going to say the nth term test applies, this series is divergent. Okay, well that's it for this video. Stay tuned for the next one. I think we'll have 1 or 2 more on the alternating series test.